Then I would like to welcome you to this second talk on piecewise deterministic Markov processes in risk theory and an application of quasi-Monte Carlo integration in this field. And today we will speak about, or I will speak about PDMPs, how they generalize the models we've seen in the first talk, and how we can approximate functionals of interest by high-dimensional integrals in the end. Yeah. Okay, so that's the program. The program for today. The quick introduction to PDMPs. Then, because we use Markov processes, we can translate expected values or transform expected values along jump times of the process into iterated integrals, and we can use them to approximate functionals of interest like ring probabilities or Gabor-Shio functions or some profit criteria. Yeah. Okay. And then, since we are facing high-dimensional integrals in the end, we need to discuss the applicability of the quasi-Monte Carlo method. Yeah. And we will see that a direct application, or if you would like to bound an integration error by means of the Cox-Matlafka inequality, the notion of the Hardy-Krause variation for the integrand turns out to be too restrictive. Yeah. And for this, we can use or utilize, or to come over this feature, we can utilize a novel concept, or due to Bausinger and Swane from 2015, who introduced a different notion of variation, or in our case, a K variation of the integrand. And we see that in this setup, we have a chance to arrive at some results, at least. Yeah. Okay. Then, what is the motivation to use these piecewise deterministic Markov processes? Yeah, we've seen in the first talk that many risk models and generalizations of it share same features. Yeah, we have finite variation sample paths, we have jump size distributions, so we have jumps, we have a jump intensity which governs the timing of the jumps. And we have deterministic components or path behavior in between claim occurrences. Yeah. Okay. Yeah, but in principle, in the past, the analysis was done for each model on a separate basis. Yeah. At the same time, we would like to have a universal framework for these problems. We would like to have processes which are still Markov, at least maybe adding some components for Markovization purposes, but not too many. And we would like to have this deterministic but non-constant behavior between jumps, and a more complex jump structure in terms of the jump intensities and the jump size distributions. Yeah, and the class of processes which is very useful for these goals is the class of piecewise deterministic Markov processes. Yeah, they were originally introduced in a paper by Mark Davis in the mid of the 80s, 1984, and then several results and also applications from stochastic control were collected in a book by Mark Davis in the beginning of the 90s. Yeah. Okay. So the idea is to have some sort of flexible process, like diffusions generalize Brownian motions, for example. We would like to generalize a little bit this standard compound Poisson process with drift setting to something more complex and allowing for more flexibility in modeling. Okay, so we start constructing a process X on a state space E. Yeah, and the feature is that the state space can be decomposed into external components, that's with the index K, and internal components with the index Y. And the idea is that the internal components, the EK, they are subsets of RDK. Yeah, so it doesn't need to be the same dimension all the time. And the external component, we have a finite set of external components. and they govern a little bit different behaviors. And the ideas for each external component, we have a rule for deterministic behavior in between jumps. We have different jump size distribution and jump intensities for each of these components, but we paste everything together. Yeah? Okay. The idea is if we fix an external component, then the path of the process in between jump times is given as a solution to an ordinary differential equation. Yeah? And we denote this, also the K is we have for each external component, we have an index K, and for each indices K, we have like ODE solutions phi K, which start at time 0 at the point Y and evolve over time. Yeah, this means the starting position is external component X for marking the type of behavior, and the internal starting position Y. Yeah, and first order ODE for this phi, so some flow of over time. Yeah, okay, this means the xt in between jump times is given in this way. We keep the external component, and in between we evolve deterministically based on an ordinary differential equation. Yeah. Next feature is we need to model the jump times. Yeah. And this will be done in an iterative fashion. Mainly we think of the distribution of inter-jump times. Yeah. This means we fix some lambda k, which plays the role of a jump intensity or hazard rate, if the external component is set to k, and then we have that the tail distribution of t1 of the first jump time is given by e to the minus integral over lambda k along the path of the deterministic component. Yeah, so this means we have an path dependent or an state dependent intensity, and okay, the state is deterministic between 0 and the first jump time. This means that's the state of the process at time s. Okay, and now if a jump is generated according to this distribution, we need to think about the location of the process after the jump. Yeah, and this is done by a jump kernel Q, which is like a measurable function in the state component E, and the probability measure on the Borel sets of the state space E. Yeah. Okay, it's possible to define a metric such that this becomes a Borel space. Yeah. Also E and the Borel sets that we have a suitable state space of the process in the end. Yeah. Okay, but the importance is the post jump location of the process. Okay, we generate a jump at t minus. The position of the process is the solution of the ODE at time t1 or t1 minus. But since it's continuous, it's at t1, and then one samples a post-jump location according to this distribution. Yeah. Now we fix the post-jump location. This means we have a new external component and a new internal component, and then we start the construction in U. Yeah. And in this piecewise manner, we can define the process. Okay, so maybe this is a nice idea. Yeah. Here we have three components, for example, the E1, E2, E3. Okay, as we start in E1, then we follow the solution or some ODE solution, then T1 forces a jump, or at time T1 we face a jump, we jump to the second component, follow an ODE curve, jump to the third component, and so on. Yeah. Okay, but the ODEs in these components do not need to be the same. The jump intensities do not need to be the same, and the distribution of the post-jump locations also do not need to be the same. Yeah. Okay, and in this way we can principally describe all the models we've seen in the first talk. Yeah, the Markov modulation means the Markov. The Markov chain governs the external states, and depending on the external states, we have different classical risk processes. Yeah. Okay. Then this incorporation of interest and inflation gives us non-constant drift in between the jump times. Or we can also incorporate some debt scenarios if we're allowed to borrow money according and pay some interest rate. This is the same idea. fits perfectly into the setup. Yeah. Multidimensional models can immediately written like, also the standard multidimensional models fit into this framework, and there are several other applications. And another one, like in life and health insurance context, also this is presented in a paper by Davis and Velekop also in the mid of the 90s. Yeah, and thanks to Gunter Leobacher for providing this plot. Yeah, also the basic idea should be fine. Now we can add some additional features. Yeah, the first thing is we can force jumps at deterministic points in time. Yeah, and this means we face something which is called an active boundary, and that's like points on the boundary of the state space which can be reached along solutions of the ODEs. Yeah, this means we deterministically reach the boundary of the state space, and then we force a jump. Yeah, or we need to tell the process what needs to be done at the boundary. Yeah, and the typical feature is you force a jump. Yeah, either in the external component or also in the internal component. Yeah. Okay, and the T star, this is like you start in state K theta, also in the point X, and then the T star is the first time one deterministically hits the boundary of the state space. And then if we force a jump, we need to modify the distribution of the jump times. Yeah, this means up to the time when reaching the boundary, we have our tail distribution from before, also the e to the minus integral over the hazard rate or the intensity, but we need to force a jump if we reach T star in time. Yeah, that's one feature. And another feature is, okay, something probabilistic just happens at the jump times. Yeah, everything in between is governed by solutions of ODEs and is deterministic. This means the only information input or new information input arrives at jump times of the process. This means one can embed a pure jump Markov process, eta, who just looks at the post-jump locations and the number of jumps. Yeah, number of jumps may be important because it's possible that the pre and post jump locations are the same. Yeah, but we have maybe a jump from the external component. Yeah, this means that can be important. Yeah, okay. This is nice. Yeah, and there is a paper, I guess, by Charcot and Skorokot who generalize or who analyze pure jump Markov process in a very general way, or on very general state spaces, and this includes certainly all the results or some basic probabilistic results on these PDMPs. Yeah. Okay. Then what else? Yeah, some basic results. Yeah, one can really show that the X is in our way, formulated in our way, is a time homogeneous strong Markov process with respect to its history. Yeah? This says that if we start in X, the conditional expectation of the process at time t plus s, where t is stopping time, in case t is finite, conditioned on the information up to the stopping time, is given by the ts. This means more or less the expected value of f evaluated at xs, conditioned on the new initial position xt. Yeah, so the ts is more or less the transition operator, one may call it like this. Yeah. Okay, so that's the Markov property, the strong Markov property in this setting. Okay, and now what is nice? Okay, that's like a family of linear operators. Yeah, in the index t, time index t. If everything is nice, then the T0 is the identity, and even this should be in the classical Markov process setting, the T is a contraction semigroup. Yeah, so these operators T form a contraction semigroup, and for these operators, one can define a generator, and the generator, we call it the capital A applied to some function f. It's just a limit, or just h to 0, 1 over h, and the the t at time, also a th should be here, sorry, applied to f minus the identity mapping. Yeah, this is somehow more or less looking a little bit like the derivative with respect time of the transition operator. Yeah, okay, and now we need to discuss a little bit the domain of this generator. Yeah, and typically, one sets the domain as a subset of measurable bounded functions, such that the transition operator applied to the function is continuous in time t at 0 from the right. Yeah, because it's not clear if we are in a failure process setting up to now. Okay, but the main feature is, or how we would like to characterize the domain of the generator A is a characterization from martingales. Yeah. Okay. If the f lies in the domain of the generator, then we can form a process mt, which is the function f applied to the Markov process x at time t minus f applied in the initial value minus integral 0 to t, and then we integrate the generator applied to the function f along also over time, evaluated at xs. Yeah, and this typically forms a martingale if f is in the domain of the generator. Yeah, but now this classical definition of the domain is very restrictive. Yeah, and that's why one typically uses, if one focuses on martingale, one uses the concept of the extended generator, and this says that a function f belongs to the extended generator if there is some measurable function h, such that f xt minus fx minus the integral over the measurable function hs, this would be interpreted as a function h of xs. The s is a local martingale. Yeah? Okay. Also the important thing is, yeah, functions f which are regular enough such that this thing becomes a martingale. Yeah? And the martingale M is called the Dynkin martingale or Dynkin's martingale. And in the case of piecewise deterministic Markov processes, one can fully characterize the domain of the generator or of the extended generator. Okay, this means, also just to tell you the feature, also the properties of the functions we need, and for these functions we can precisely write down the generator. Yeah, the idea is we have the Markov process X or a piecewise deterministic Markov process X. Then we need that the expected number of jumps up to time t is finite for all points in time t and all possible starting points x. Yeah, and then we get that the function f belongs to the domain of the generator if the function f is we start here, is absolutely continuous along the ODE solutions, yeah, or the curves of the ODEs. Then we need some sort of continuity in the initial value. This means we continuity from the left as well. This is the message. Yeah? We start in some point x, go backward in time along the ODE curve, and go forward again with t equal to 0. And we should have some left continuity as well, yeah, because the mapping t to the function f along the ODE solution, this is forward in time. Yeah, this means we need to move continuously forward and backward in time along the ODE curves. Yeah. Then, okay, this is regularity in principle for the if nothing happens. Yeah. Also inside the state space. And then we need something if we have an active boundary. For ending up with a martingale, if we would start at the boundary, we should have a constant conditional expectation in the future. Yeah? This means that the values of the function at the boundary should match the more or less the average value after this first immediate jump in the beginning. Yeah, this means we have an immediate jump because we start at the boundary, and then we jump somewhere else. Yeah, somewhere else governed by the distribution Q, and we need to fulfill this integral equation at the boundary. And then we need, for ending up with a local martingale in the end, we need some integrability assumptions, and this means the P is here, that's a random measure generated by the buffer of the process, and this is given by, okay, we count the number of jumps which occurred up to time t, and then we check how often the post-jump location landed inside the set A. Yeah, and localizing means that more or less the expected value of the absolute value of differences of post-jump minus pre-jump value is bounded. Yeah, so this is the integrability condition is hidden here along the paths. Okay, and if the function is regular enough, fulfills these 4 points, then we can write the generator applied to the function f in the following way. The x here, that's the vector field. This means that's the sum of the partial derivatives into the directions or into the components of x times the drift. Yeah, the drift is, we go back, the drift is exactly the function gk evaluated in x. So this is some vector field. That means that's first order differential operator, and then we have this non-local term, and this means lambda is the jump intensity, the post-jump location, pre-jump location, and we integrate against the jump size distribution or the post-jump distribution if we start the jump in x, yeah, and land at y. Okay, that's the form of the generator. Now, okay, this means we can utilize this generator and the martingale from before, because now we know, okay, we have the f, so we can build up a martingale, we can plug in here the form of the generator, and we know that this is a martingale if f is regular enough. And this shows something in diffusion models that's called the Feynman-Katz formulas. And yeah, we can use the same concept also for our type of processes. Yeah, and the idea is the following: we have two functions, L and C, and L is somehow a running cost function of the process, and the C is a cost function for jumps from the boundary. Yeah, also two types of cost functions. Yeah, something as long as the process runs over time, and something which just accrues if we jump from the boundary. Now suppose we have a function f in the domain of the generator, which is integrable in the correct form, that the limit t to infinity of the expected value f of xt vanishes, and the function f solves the following equation. Yeah, the generator applied to the function f plus this cost function L here to 0 for x inside the state space, and at the boundary we fulfill more or less the integral condition from the domain of the generator, but in addition we have the costs at the boundary. And if a function fulfills inside the domain or inside the state space this partial integro-differential equation and this integral equation at the boundary, then the function f admits a stochastic interpretation as the expected value of the cumulated costs over time plus cumulated costs when jumping from the boundary. Okay, this means if you remember the ring probability solved an integro-differential equation. Yeah. Now this means the L, in this old equation, the L is 0, A is the generator of the compound Poisson process, and that's it. Yeah, because actually we know from the Markov property that the ring probability itself forms a martingale. Yeah? This means the ring probability needs to solve the equation generator applied to ring probability or survival probability equal to 0. Okay, this is all the IDE characterizations we saw for functionals in the first talk, like for the Gabor-Shio functions, for the survival or ruin probability, in principle based on an argument like in this theorem. Yeah, regular enough function, integro-differential equation, and the stochastic interpretation. Okay. Yeah. Now we look at the more specific setting, or at cost functionals which are in the spirit of these Gabor-Shio functions, or the ruin probability, also these ruin related quantities which are interesting for us. And for this we assume that the state space or that at the complement of the state space the process is absorbed, but that we may jump into this absorbing state EC, yeah, as in the complement of the state space. And then the idea is, okay, as long as we are in the fine state space E, we have a running reward or a cost function L as before, which is 0 in the absorbing state. Yeah, and then we have a terminal cost function, which is just defined or non-zero on the really absorbing part of the state space. Yeah? And then we look at the function v of x. It's like, in principle, we start with this with a function like this, and yeah, that's the expected value over all cumulated rewards or costs over time, plus this terminal cost function if we jump or if we reach the absorbing state. Yeah? Also the tau is the stopping time, the first time the process enters the absorbing state. Yeah? And we just accumulate rewards or costs up to this stopping time tau. Yeah, so in the risk theory setting, this is the time of ruin. Yeah, and now the idea is to determine the v by means of integration, yeah, instead of the integro-differential equations. Also we know that, yeah, we may, or we can actually write down equations like this for the functional f, for the functional v, but we would like to complement the integro-differential equation by the iterated integrals in the end. Yeah. Okay, and the procedure is as follows. Yeah, we mentioned in the beginning that the only stochastic input happens at the jump times. Yeah, and that actually looking at the process in discrete time, just at the jump times, at the post-jump locations, we face a Markov chain. Yeah, more or less, or a Markov chain in continuous time, but also with an uncountable state space maybe. But we exploit just the Markov property of this post-jump process. Yeah, and the idea is, okay, we have our functional, and then we look at the process up to the first jump time and split off the integral here from 0 to the first jump time, from the first jump time up to the time tau. And then we just check what may happen. Yeah, okay, up to the first jump time we collect some rewards. Yeah, if the jump happens before entering the absorbing state, okay, we can continue. This means we still have the integral from t1 up to tau open, but we need to rescale a little bit. But we face, because of the Markov property, we face the same process, but just with another starting point. Yeah, this means we face the same functional again, but with a new starting point. Yeah. Okay. Then, if ruin happen, or ruin, if we enter the absorbing state, then we accumulate or generate rewards just up to this ruin time, and then we face this cost function from the absorbing state psi, but now along an deterministic path. Yeah, because it happens before the first jump of the process. Yeah? This means we deterministically hit or enter the absorbing state. This is this term. Yeah? And last option, we enter absorbing state by a jump, and then we generate this thing, but no continuation values because we stop everything. This means now we collect all the all black terms, everything we generate up to the first jump time in the function h of x, yeah, and we define the operator g just as the expected value of x of this continuation value here. Yeah. This means the h collects everything up to the first jump time, and the g operator pushes the problem forward in time by one jump, or by one jump time actually. Yeah. And now we can iterate this one and end up with a representation like this. Yeah. If we look at n jumps, we shift the remaining problem from tau n or tn up to tau into this functional gn v, also n times applying the g operator to the function v, plus we collect things over time, yeah. Also the h of x between 0 and t1, g applied to h, this is the rewards costs between t1 and t2, and so on, yeah. Okay, but we see, okay, if we apply the g, here we have an integral with respect to time and integral with respect to the post-jump location. The h is principally an integral with respect to time. Yeah, this means here we have an 2i minus 1 dimensional integral to calculate, and one can work out the structure of this integral. Yeah, okay, and it looks like this. If we start in x0, the h is this cumulated rewards between jumps function, and we apply this gi minus 1, as the gi I minus 1 times here. Yeah? This means in total we face I jumps. Yeah. Okay, and now, yeah, as mentioned before, we have jump times t1, t2, t3 up to ti minus 1. We have post-jump locations of x1, x2 up to xi minus 1, and the integral inside the h. Okay, and what happens along a path? We start in x0, we jump at t1, we jump to x1. In x1, we restart, also we deterministically move the path up to time t1 along the ODE, yeah, up to t1. Then we jump from x1 to x2. Again, we move along the ODE and so on. Yeah. And the last jump is like from xi minus 2 to this xi minus 1 in the end. Yeah. Yeah. And here's the xi minus 1. It's the post-jump location after the I minus 1 jumps. Okay, we can restructure a bit, and this is the integral. And here we assume that the inter-jump time distribution, this piecewise defined jump time distributions allow for intensity. Yeah? Just to compactify a little bit the notation. Yeah? But this is actually the form of the integrand. Yeah? We have here, okay, the intensities. Here we have always post-jump locations. Yeah, here we have jump size post-jump distributions which depend on the ODE input, the jump time, yeah, and so on. Yeah, and this in a very nested manner. And finally the h, but the h can be recomputed. Okay, this means the integrand is complicated and not, yeah, often a priori easy to analyze form. No. Okay. Why can it still be useful to exploit this representation or approximation with these many integrals? Huh? Okay. The basic problem is that the integro-differential equations are, they can be solved by some finite difference or finite element methods inside the domain. Yeah, but fixing a bit the boundary conditions is a little bit hard, yeah, because the boundary conditions are given as solutions to integral equations. Yeah, this means we can the basic idea is we combine these two concepts. We do the approximation with these iterated integrals at the boundary for computing boundary values. and use the integro-differential equations for computing the function of interest inside the domain or inside the state space. Yeah, and in the third talk, I would like to show you some examples where this really works out. Yeah, or where this is very beneficial. Okay, and now we may have a look at the what can be done or can be said on the evaluation of these integrals. Yeah. Okay, I think Girai in his series of talks presented lots of basic results on QMC integration, and yeah, just remember the basic idea. Yeah, the standard setting is the numerical approximation or evaluation of an integral over a function f over the unit cube in s dimensions. Yeah, so s in our situation would be 2i minus 1. Yeah, okay, but we evaluate this by just evaluating the function at points x1 up to xn and then taking the average. Yeah, okay, and then the classical result is stored in the Cox-Malavka inequality. This means we take a point z x1 up to xn from the unit cube, and this should be the approximation for the integral, and the absolute value or the error can be bound by the variation of the integrand f times something times a measure on the quality of the points we use. Yeah, and the measure is called in our case the star discrepancy, and that's more or less a distance, or loosely speaking a distance to uniformity. Yeah, so we have these n points and we would like to place them in the unit cube, and then we check how many points are inside the set, or take the average. Also the fraction of points which lie inside the set J, subtract the Lebesgue measure of this J, and take the supremum over all possible. In this situation, X is aligned boxes, one vertex and 0. Okay, so the idea is you fix certain sets and then check of the correct fraction of points in relation to the Lebesgue measure of this set is somehow small. Yeah, okay, but this is the basic bound for the error of the integral, also for the integral approximation. Now, yeah, the problem is we have a very complicated integrand, and the variation in this case it's this Hardy-Krause variation is not easy to handle, and many even simply looking functions obey an unbounded variation. Yeah, okay. This means, the error bound is nice because we can separate the influence of the points we use and separate the effect of the regularity of the integrand. Yeah, and as mentioned, the variation which is used here is not so, is complicated to analyze actually. Yeah, and in the best situation, this Hardy-Krause variation is given in this form. Yeah, so we look at partial derivatives, first order partial derivatives of the integrand with respect to subsets. Also the U is like we have in dimension 1 to S. We take some directions stored in U. We take the first derivative in all these big directions, fix the remaining arguments of the function like at the end of the box in 1, and then we need to somehow bound this or determine, analyze this type of integrals, over all possible selections of directions. Yeah, okay, and this is not so easy to handle. Yeah, okay, but there is a different approach, and this is something we can apply, later on. And the idea is we would like to have a similar bound as before, that integration error, the same integration rule, so just average of a sum. And the bound is still, so the error is still bound by something of the form influence of the function and quality of the points. Yeah, and here that's called decay variation in this thing. Yeah, and the idea is the following. Yeah, we will use also Bausinger and Swane presented or introduced this concept for different possible kind of subsets of the unit cube, but here we focus on convex subsets of the unit cube. Yeah? And that's they are stored in the capital K. And then the idea is, okay, we introduce simple functions based on the convex sets, and they are just piecewise constant on different convex sets. Yeah, so a function f is called simple if we can represent it as such a sum. Yeah, with weights alpha I and just indicators of the different sets ai. Yeah, and for these simple functions, one can define some sort of variation. Yeah, and that means that this representation doesn't need to be unique. Yeah, this means we look at the smallest value we can achieve by picking different representations of functions f, and the quantity we minimize is just the sum over the absolute values of these weights, the alpha i's, and the function hkai. But this is in principle 1. It's 0 only if a is the empty set or A is the complete unit cube. Yeah, as this is actually 1, and this means we just sum up absolute values of these weights. And now the next step is, okay, we fix functions f which are nice enough to be approximated uniformly by sequences of simple functions. And for these functions, there are sometimes, also I think in Bausinger Swane, that's the V infinity of K set of functions. One can define a variation. Yeah, and that's the K variation of a function f is more or less the smallest value we can achieve here along the sequence of approximating functions. Yeah, so we start, we pick a sequence of approximating simple functions, and then we look at the lim_inf of the variation of these approximating simple functions, and we take the infimum over all limiting values we can achieve by choosing different approximating functions. Okay, this is but this is something not obvious how to compute this thing, but the nice results, which is also shown in the paper, is that if we face a 2 times the differentiable function f, this k variation can be bounded by the following expression. Yeah, also by construction, if such an approximation procedure works, the function f is bounded. Yeah, this means and then this k variation can be bounded by the difference of the sup and the inf plus a norm, or a norm on the second derivative. Yeah, so here we have the Hessian matrix, and we take the operator the operator norm on the second derivative. This means instead of needing to be able to control all possible first order derivatives, we need to control second order derivatives, but in a more compact way. Yeah. And then one also gets some sort of Cox-Malavka inequality. Now in this form, this means we bound the k variation by this expression times again a quality measure on the point set, the d tilde n, and the d tilde is now not the star discrepancy, but it's the isotropic discrepancy which fits to the convex functions. Yeah, before we took the supremum over the differences of proportions and Lebesgue measure over the boxes, and now we take the sup over the convex sets. And this gives, or this defines the so-called isotropic discrepancy. Isotropic discrepancy. Okay, and then a result which can be found in the book by Niederreiter and Kuipers, for example, or also in the book by Leobacher and Billichshammer, is that the isotropic discrepancy can be somehow squeezed into two terms depending on the star discrepancy. Yeah? But it becomes larger, obviously. Yeah? This means we can bound maybe, because we can more easily or get more functions which obey an finite variation, but we need to at the cost of a larger quantity here. Okay, yeah, this means we need, if we would like to apply this concept, we need to somehow get smooth coefficients, at least C2 coefficients inside the integral. Yeah, okay. So this means these things here as functions, also all the terms here as function in the x's and the t's should be C2 after transformation to the unit cube. Okay, and this is now, we will see that's somehow feasible, but it's very interesting which problem or the features which need to be considered. Yeah, and the first thing is the presence of the ODE curves. Yeah, the ODE curves appear in the jump post-jump distributions. They appear in the hazard rate or in the density of the interjump times. This means the pre-jump locations and the jump times are present as an argument in all of these expressions. Yeah? And if we take the derivatives, we face first, second order derivatives with respect to the time t of the ODE solutions, second order derivative, and also we get like derivatives with respect to the initial value of the ODE curves. Yeah, and at the same time they are weighted by the probabilistic ingredients. Yeah, also the jump size distribution, also the post jump distribution and the jump intensities. And this means that the ODEs or the behavior of the ODEs needs to fit together with growth properties or smoothness properties of the probabilistic ingredients, such that in the end we arrive at smooth integrants. Yeah? And now, as we will see also in the next talk, if we take these many generalizations of these risk models, we immediately have these continuities there. Yeah, either we get indicator functions in the drift, or we have just one times differentiable drift coefficients, but not two times differentiable drift coefficients. And this means one needs to smooth the coefficients. Yeah? But when smoothing the coefficients, one needs to be careful, because we would still like to approximate functionals for the underlying original processes. Yeah, this means we need to smooth such that if we smooth finer and finer, we still achieve an approximation and some approximation of these functionals. Yeah, and now we have two opportunities. Yeah, we smooth the processes, and then we get a sequence of piecewise deterministic Markov processes with smooth coefficients which approximate the original process X. Yeah, and now we can argue in a qualitative way and say, we can somehow ensure that this sequence converges in a weak sense to the limit or to our original process, and at the same time we get convergence or for suitable expected values. Yeah, it's a qualitative result, or we show it directly by hand. Yeah, so we calculate these functionals for this approximating sequence, and then really show that we have convergence of these functionals. And a result which can be used to answer the first question is the following. And here we cannot face the most general setting of a PDMP. Yeah, we need to have a failure setting here. Yeah, this means we should not have an active boundary. So no jumps at deterministic points in time. That's the most crucial thing here. Yeah, and this is the limiting process. Yeah, and now we take or have a sequence xn, also of failure type PDMPs, and with characteristics phi n. This means the ODE solutions, or yeah, the vector fields, the jump intensities, the post-jump distributions, and we have that the vector fields, or these ingredients of the ODEs, the functions Gn converge against G, the intensity functions converge against the target intensity lambda in a uniform way in the state space, and we have some sort of convergence of the post-jump distributions written like this here, yeah, and also the initial values may converge if they are chosen to be random, yeah, and if we fulfill 1, 2, 3. This means the coefficients of the processes converge in the correct manner. Then we have convergence of the sequence of processes against the given process X. Yeah, and we get if the cost function or reward functions are bounded and continuous. This can be maybe via localization, maybe relaxed a little bit. We get convergence of our functional v of x. Yeah? Here along the x ends, and here for the original process x. Okay, this is just a qualitative thing. Yeah, but we know if the coefficients are smooth in the sense that we have C2 integrand in the iterated integrals from before, then we know we can approximate these things here using the quasi-Monte Carlo integration. We can bound the error, and we know if for n to infinity that we can approximate the original function. Yeah? So this ones approximate this one with by the QMC integration, and the second approximation step is in the smoothing. Okay, another opportunity is to do everything by hand. And for example, we can look at a process like this. Yeah, this means we have more or less compound Poisson setting. Here, that's just compound Poisson sum. And then we have a drift function which depends on the state of the process. Yeah. Okay, and the idea is if the process enters or reaches a level B, we switch off the drift. Yeah, this means the process X is kept below some value B, and if it is negative, we do not need to declare ruin and can continue, but we need to borrow money to be allowed to take this debt, interest at rate rho, but just if we are negative. Yeah? And this means if we are too negative, so this means if the process is below minus c divided by rho, we get in total a negative drift and everything is over. Yeah? But we can allow for a certain depth, limited depth, and look at this process. Yeah? And now we see, okay, we have the indicator function here. This means the function c of x, or this g of x driving the ODEs. Now, yeah, this is discontinuous, obviously, in from the left coming to B. Yeah, and it's continuous in 0, but not differentiable in 0. Again, because of the indicator function. This means there is no chance to have C2 coefficients of the process. Now, yeah, okay, but what can be done? We just smooth a bit the indicator functions and paste the parts together. Yeah, this means we have the function C in between epsilon and B minus epsilon. Then we smooth a bit this reflection in B by in this way. Yeah, if we are below 0 and slightly above this minus c divided by rho, we take the original one and then we smooth around 0 such that between this and this we are C2 in 0. and otherwise we set the drift to 0. Okay, at the same time, we smooth the cost function, in the same manner more or less. And what is nice, in this way, if we calculate our functional v of x as before, once for the process with the smoothed coefficients in epsilon, and the v for the original dynamics here, we can directly show that this uniformly converges as epsilon tends to 0. Yeah, so this would be not to use the general result on Feller PDMPs, but to do everything by hand. Yeah, but for an example. Yeah. Okay, that was the main idea. Oh, okay, then certainly there are alternatives for these iterated integrals. One can do directly Monte Carlo simulation of the paths, and then we do not need any regularity of the integrand. This is clear. Yeah. And the length of the confidence interval is more or less 1 over square root of the number of points we choose. Yeah. One could also use more advanced techniques from numerical analysis, such as these Gauss quadrature rules, or in higher dimensions. But then, if we compute approximate integrals by such a Gauss rule, we get similar, a bound depending on the norm of the function and something in the number of points. But for getting better bounds or really improving bounds, we need to have even more than 2 times differentiable integrals. Yeah, because here because m tilde we have more or less kappa divided by s, or s divided by kappa. Okay, but this means we need for applying these more advanced cubature methods, we need to have even more regular integrals. And also we need to use lots of points. Yeah, in our case, if we look at our process along the jump times, we may need to observe the process or calculate something for the first 200 jump times, and this means we have then a 400 minus 1 dimensional integral to solve. Yeah? This means S becomes very quickly very large. Yeah? And then one can hardly afford to plug in many points for each dimension. Yeah? For the Gauss rule. Okay, so this becomes at the same time very costly. Yeah. Okay, then some references. Yeah, as mentioned, there is the book by Davis, or the original article. The book is called Markov Models and Optimization. It covers all the basic results on PDMPs and also results and concept from stochastic optimal control for this class of processes. Yeah, also optimal stopping and or as common control problems and these things. Yeah. Then the ideas concerning the approximation of the processes and of the cost functional is out of a paper with Peter Kritzer, Gunter Leerbach, and Michaela Sölvini. And the mentioned result or presented result on this K variation is due to Bausing and Swanne from a paper from the year 2015. Yeah, okay. Then thanks for your attention.